Hello everyone, my name is Cora and I am the treasurer of the International Conference of Physics Students Puebla 2022. It's a great pleasure for me to introduce our next guest speaker, who is going to give us a talk about the new international systems of units and quantum mechanics.
You are muted, Cora.
Thank you. Hello, everyone, again. Dr. Romero's areas of expertise are those in quantum physics and thermodynamics. He is a member of the Institute of Radio Astronomy and Astrophysics and the Institute of Material Research, both part of UNAM from 1999 to 2003. He functioned as chief of the Department of Complex Systems at UNAM. His efforts as an educator have contributed in the development of countless PhD interviews, but also in the achievement of multiple laureates in the international physics community. He has published 90 articles, which has been cited 1,200 times overseas. Among the awards and are the National University Distinction for and the Mexican Society of received PhD
Okay, can you hear me? The sound was a little bit noisy. Couldn't hear very well. But, probably it was me. I don't know if people can hear my voice clearly.
Yeah, I think it was a problem. I think a problem with Cora's microphone, but we can fix it right now.
Okay, but can you hear me now? So can I start?
You can start. Yeah, sure.
Okay. So thank you very much. Thank you very much for the invitation. And it's an honor to be here for sure to share with you a little bit of physics, which is what I decided to do. And you know, the topic, which is to talk about the international systems of units. It is I do not work on the international system of units, but I do work on quantum mechanics and some of the aspects of the changes of the international system of units, of course, is related to the type of research that I do. And so since it's always complicated, these kind of conferences, and I understood that there are students from all, from first years to perhaps to PhD students, I decided to make probably, I hope it's not too elementary, but more like a conversation, something light and something that of course we can go deeper if you ask me, but something that should be understood by a first year student and more to talk about the relationship, some things that we do not typically discuss, is my experience in courses. And so the idea is, what is the relationship with the new international system of units and quantum mechanics? And probably you know, some of you, but most of you probably don't, that in May 20, just 3 years ago, we have a big change in the way in which we define the units in the international system, which I will tell you a little bit more ahead. And so, as you know, the international system of units, probably some of you know, is made out of 7 quantities: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. However, the meter and the second had already had a change in terms of quantum mechanics and special relativity, but recently the changes were in the kilogram, the ampere, the Kelvin, and the mole, and they were changed now by constants. Really very strange. Where at first sight that we now, instead of talking about kilogram, ampere, Kelvin, and meter, the international system of units is based now on Planck's constant, the charge of the electron, the Boltzmann constant, and the Avogadro's number. I will focus today only on Planck constant and in some of the units. So quickly, as you know, probably, there is this organization in Paris, which most of the countries in the world belong. Mexico is part of this organization. Is the General Conference on Weights and Measures, and these are the units. You know, kilogram is unit of mass, meter units of length, second unit of time, ampere electric current, Kelvin temperature, mole the amount of substance, and candela luminous intensity. I will only talk about these three, and as I say, I don't want to be complicated, and I would like that all students understand what I say instead of overwhelming you with complicated concepts that we will not have time to discuss at length. So again, what is measuring? You know, why we need an international system of units? And you know, here I have a balance to measure weights, a ruler, a clock or a watch, is a multimeter and a thermometer, for instance. And as you know, measure is comparing. So we have to compare with something in order to say that something is 10 meters. So we have to say what a meter is, or something what is 10 seconds, what is a second. And so we need to compare, and therefore we need typically we think that we need a reference prototype to measure. And but quickly, units are arbitrary. You know, these are completely arbitrary, and they are inventions of people in a historical moment, born out of the need to bring some order to our commercial, industrial, technological, scientific, and social relationships. Not only, you know, this is important now that we are aware that we are not only doing things scientifically, but there's a lot of interest in that we also participate in technology. And of course, this has a lot of impact in our social relationship. And so they are completely arbitrary. And why they were like that, I would like to give you just a bit flavor about it. But the idea is that once we develop or create a system of units, we must commit ourselves to use this system of units. And you have to say we have to agree, everybody, otherwise it would be a complete mess everywhere. There is some mess, right? Because in some countries use other units, but most of the world use these units at least for commercial and scientific relationship. And so a brief history of the second, let me tell you. You know, it is lost in history how the second arose. It is known that the Egyptians, Babylonians, Greeks, some were there. And I haven't looked very deeply, but it is hard to know when it was decided that the day was 24 hours. So the first clock that we use is, let me see, something is missing here now. It was that the Earth was our first clock, you know, because the Earth goes around in day and night. And so it was decided it was 24 hours, these numbers. And then an hour, 60 minutes, and later the second minute, which a second small part was the second, right? And of course, how we fix this is complicated. And the first clocks were invented in the Middle Ages. And as the point is this, anything that oscillates with regularity is a clock, right? And in 1656, Christian Huygens invented the first pendulum clock. And we still have pendulum clocks in, you know, these very expensive clocks now because they are like pieces of museums, the pendulum clocks. However, until 1960, so recently, you know, I was born in 1960, a second was defined in this very strange way. It was defined with the reference of a solar year that occurred starting from January 1st, 1900. I never understood how this is done, but somehow it was possible to make a reference with the year that occurred in 1900s. The reference was 1900, but this was put in 1960s. However, this was complicated, and here's when quantum mechanics entered in our units for the first time, and it was with atomic clocks. In 1967 was the first atomic clock, and later in 1997 it was fixed again using a transition between two hyperfine levels of cesium-133. So 1 second is this big number of this exact number. The point is that 1 second is this exact number of periods or of oscillation of the transition between hyperfine levels. And I would like to talk about this. I will concentrate later on how this, why we're talking about this with a little bit of elementary quantum mechanics. And so the first atomic clock was like this, and in 1997, and let me tell you, I believe that very soon we will change the second to something even more precise, something with more figures. Okay, so I will wait later to tell you a little bit more about this atomic clock. And so here is just a picture, you know, that anything that oscillates like a tuning fork could be used as a clock, as a watch. And you know, we have these ancient and very expensive now pendulum clocks, but let me tell you, they were still used until, you know, in the 20th century. It's amazing as references. Of course, the Earth was our first clock. And, you know, now we use all these quartz watches. And it is because there is a tiny crystal of quartz that oscillates, that, you know, with electricity, that you have a battery, it oscillates very precisely. And they are extremely precise, but not completely enough for our needs now. And, you know, one of the modern atomic clocks, this is, of course, there are atomic clocks that are much smaller, but one of the recent one, atomic clocks, looks like this, and it's just made out of a lot of lasers and ultra cold gases, which is the field in which I work. These are gases, of atomic gases that can be cooled to very, very low temperatures in the nanokelvin, hundreds of nanokelvin, and that's another topic completely on its own. And so the meter, how came the meter? The cubit, which is the size is from the elbow to the hand, I don't know, to the point of the elbow. Of course, we have all different sizes of cubit, but it was used the cubit. It was the cubit of someone. And then the foot, I think that the foot was one king that was a large foot because it was like 30 centimeters. The yard, the inch, the miles, the leagues, and these are typically English measures. Of course, we still use the legua in Spanish, right? And in 1799, the metric system was initiated in Paris. Somehow the French Revolution brought a lot of interest in fixing a unit of length. And the meter, you know, when I was a kid, I learned that this was the meter. I remember very clearly that the meter was defined in this way, as 1/10,000,000th of the length of an Earth quadrant, right? So that what is a quadrant is the fourth of a meridian is the circle that goes around the Earth and passes through the North Pole and the South Pole. And that's why the circumference of the Earth is approximately 40,000 kilometers. But that was the point. The French said, let's say that the meridians have exactly 40,000 kilometers or 40 million meters. And so the meter was this fraction. And it was a competition with the yard because it's very similar to the yard. But the French wanted to use also a decimal system, as you know, to break everything in tenths of things. And in 1889, this was corrected, and they said, let's make a prototype in Paris, which is a bar of 1 meter, and that was the meter, that bar in Paris of 90% platinum and 10% iridium. And so it was since 1889. And in 1976, this was changed, again now using quantum mechanics and special relativity. And here I make a pause very, very quickly. Light travels, so this is the point. This is something very strange the first time that we hear it, and it is that the speed of light is the same for everybody, for any reference frame, it is the same, which means that if I go in an airplane and turn on the light of my cellular phone, the light goes at 300,000 kilometers per second, approximately, actually this number exactly, and someone on Earth sees at the same speed. So it doesn't matter that I put the light in an airplane that goes to 1,000 kilometers, the light doesn't go 1,000 kilometers faster than with the reference that someone is standing on Earth. It is exactly the same, and that's very strange, right? So it is a universal constant, and we have to understand special relativity, and there are it's a lot of fun to learn this in our courses. But now here, and of course, the questions we can go deeper. I don't want to dwell into this more. Simply, we know that it's a law of nature that tells you that the speed of light is the same for all observers, no matter what their state of motion. It's a complicated law, and so that changes our concept of space and time. And because of this property, then what was the speed of light in terms of a meter that we define completely arbitrary? So it was a number with a lot of significant figures. So what they did in 1976 was to say, no, it's going to be an exact number of meters. So the meter was changed slightly. And so it is exactly 299,792,458. So essentially 300 million meters per second, right? But it is exactly this number. And for this, that the light travels in 1 second, and therefore you need a second. And you already defined the second with a lot of figures. So you use the second that it was already defined, and then you speed of light, and with the speed of light, you define the meter, right? And so this is not very complicated. And so now this number is exact number of meters. So what we changed was the meter using a natural law. And so, and the kilogram was a mess, was even worse. So, no, the kilogram was terrible. In the 1700s, in France, one of the kings, Louis XVI, there was a lot of frauds like in our markets, so that they don't give you the exact kilogram. But this is all, everybody tries to make an advantage. And so there were a lot of frauds in the markets in Paris and in transactions. And so they defined something that it was called originally the grave, which is our kilogram. And so they said, a grave is 1 liter of water at the freezing point. And then later it was changed in the French Revolution again in the 1700s, that a gram was a cubic centimeter of water at 4 degrees centigrade. You know, when I was young, and the first time that I realized that a liter of water was a kilogram, I thought, oh, what a coincidence. No, it was defined like that. A liter of water is a kilogram, more or less. But this is not exact. And again, in 1800, it was changed by a piece of platinum, by a piece of junk of platinum. And look at this, in May 20, 1875, the meter convention of 17 countries decided that the kilogram was the IPK, which is the international prototype of the kilogram, which is a piece of metal that it was kept in Paris, a 19% platinum and 10% iridium. And it was like that until 2019, until 3 years ago. We still use the kilogram as the reference to that little piece of metal in some place in a basement in Paris. People like to say that because it sounds fun. And now we change it to something based on a Planck constant, really to use in terms of a watt or a kilo balance, which I will tell you briefly about it. And for instance, this is the picture of the kilogram. This is a very famous picture that you can find everywhere. You see, this little piece is the kilogram, which is about a piece like that, like 10 centimeters big. It's not very large. It's made of platinum and iridium, so it's not very big. And so this was for hundreds of years until 3 years ago. You know, we are in the century of quantum mechanics, and it was still the kilogram, a piece of junk in Paris, of course, taken care with 3 bottles of glass at high vacuum and so on, but this thing still evaporates. So I was losing grams. It was losing weight, the kilogram. And this was an embarrassment for the scientific community. I happened to have a friend who was in the convention, and it says that it wasn't very easy these 3 years ago, that there were some countries that were not happy with the change that we use now with the Keeble balance, okay? So I will tell you about the Keeble balance, but this is the Keeble balance. It's a picture of the Keeble balance, and it's a balance. You see this circle is like it's something that it has a rope, of course, a rope of, I don't know, this plastic material is very fine. And on one side here, you put the weight that you want to weight, and all the rest of the apparatus is to compensate the weight and to say what is the kilograms that what you put here, it has. So now it turns out that that instead of having a piece of junk like this, now we have to have a Keeble balance. We cannot have a Keeble balance in our home, of course, or in the markets. And so, you have these organizations, every country has this office of weights and measures. We have one here in Mexico in Querétaro, Centro Nacional, I forgot the name. It's National Center of Measurements. It is something that belongs to the government, and it is in Querétaro, in state here in Mexico. And so we will have probably soon here in Mexico a Keeble balance like this, very sophisticated with lots of lasers and so on and so forth. I will tell you a little bit more later on about how the Keeble balance, not how it works, but something a little bit about it. And so now I like to, as I said, I like to have a conversation with you instead of putting you a lot of equations and so on. But let's not forget that since we're trying to explain nature and we need measurements to describe, and we use mathematics, first of all, to understand that we understand humans, we understand and describe our environments and surroundings using concepts, images, and words. Right now I'm using that. I'm using words, I'm using images, I'm using concepts, which are mental constructs. So it goes through us, the laws of nature. However, you use the powerful language of mathematics. And this is, I'm talking here to people that do physics, and so I don't have to dwell a lot of about this, but when you talk to other people, you have to convince people. That's why it's very hard for us to communicate with people that are not in our field, that are not scientists, that we need to use mathematics. There is no way. Otherwise, we cannot talk to the Chinese or the French, or if we came people from other planets, we will need to use mathematics. And so the laws of nature are expressed by means of mathematical equations, and we cannot avoid that. And therefore, in this regard, what is quantum mechanics? Right? So quantum mechanics is a theory. This is very important, this phrase that I'm going to say here, just again to have to say, especially to very young people, that it is the theory that not only establishes that the universe is made out of atoms and molecules. This is a phrase that I stole from Richard Feynman, Richard Feynman, the greatest theoretical physicist in the United States. He said this phrase, that the greatest discovery of humans, is to discover that the universe is made out of atoms and molecules. But the point is that we know the laws that govern or that describe the motion and the behavior of the atoms and molecules, and that's quantum mechanics. That's what he was referring to. So quantum mechanics is the best descriptions of nature developed by humankind. And this phrase, that the universe is made out of atoms and molecules, is very strong, because we have never gone beyond the moon. So few people have gone to the moon. Now we send robots to Mars and other planets around the world and so on. But so we really haven't been anywhere but outside the Earth. We have been in the Earth, on Earth, for these few hundred thousands of years that we have lived. However, we are so arrogant that we believe that the whole universe is made out of the same atoms and molecules that we can find on Earth. That's a very arrogant and very deep and very profound statement that we humans have made. But that's what we believe. And this is what quantum mechanics is all about. And not only that, it is the best description of nature developed by humankind. And so when people ask you, so why is so important about humankind? tell them that our modern life of the 20th and 21st centuries, I say 20 because I was born in the 20th centuries, and so somehow I feel that I belong to the 20th century, but now I'm in the 21st century. This would not have happened without quantum mechanics. Your cellular phone is one of the most highly and amazing device that humans have developed, not only to have fun and talk to our friends, but it is a piece of quantum mechanics that is truly amazing. But so you can tell people, your cellular phone, or your communications, your computers, your microwave oven, the laser, and all the modern medicine that now we have a lot of surgeries without the use of the knife, using lasers and so on, is quantum mechanics. So everything that is in our modern world is quantum mechanics. Okay, we have to say that very strongly to people. And this is the theory that establishes how everything is made out of atoms and molecules, and it tells us how the laws it tells us the laws that govern the atoms and molecules. Is sounding my phone, but I cannot answer now. And as you know, unfortunately, right? Unfortunately, there are many people that say the quantum mechanics cannot be understood. I totally disagree with that. It can be perfectly understood. The problem that it has. So we have to get used to use quantum mechanics. That is the point. But the point is that there are some aspects of the theory that the theory explains the behavior of the atoms contrary to our intuition. So the theory is not in agreement with how we see our big world. My hands, the airplanes, cars, and so on. So because of this problem, we believe that we are correct our senses tells us that quantum mechanics is incorrect. Some people believe that. I don't. I am completely convinced that quantum mechanics is perfectly understood as a theory, and of course you have to get used to that. And but maybe they are right, and this theory will just be a temporary theory that will be changed in the future. I don't know, but right now it is the best that we have, and its impact is just unbelievable, right? Just your cellular phone will not exist without quantum mechanics. So I don't have to convince you much more of this. And again, I would like to review just a couple of formulas for you to see how with little things we can say a lot of stuff. So I just put here in small formulas the F equal to ma, Newton's formula, Newton's force. But if you give me the precise force, I can tell you a lot of things about our surroundings. For instance, all the work of Newton was to say what was the force between the planets and the stars, which is the gravitational. I didn't write it, but it is the product of the masses of the two bodies divided by the distance between them, square, times a universal constant, another universal constant. And with that, we can explain essentially absolutely everything that happens. For many things, we don't even know general relativity. Now that people send these probes to the space and so on, with F equal ma, we can explain it. Of course, there are corrections of general relativity. But so this is a very powerful little formula. The other one is this one just because it's so famous, but I really like to go back right away to this one. That the speed of light is the product of the wavelength times the frequency, and you will see why I want to insist on this, and to insist that light is an electromagnetic wave. For advanced students that are listening to me, this is probably very, very obvious, but even if it's obvious, we have to reflect a little bit about it. And remember, the speed of light is exactly this number. It doesn't have decimal points. No, it is exactly this, and therefore, if I know the second, I know the meter. So this really defines the meter, right? The speed of light. So it's an exact number because it's a universal constant. We should put 1, but then we will have to change all the units. That would be crazy. But we should actually think of doing that. And let me see. No, I'm going fine with the time. I don't have to rush. And what is an electromagnetic wave? Well, if you have seen Maxwell's equations and so on, it's easy for you to say, oh, of course, it comes out of Maxwell's equation. But if you think a little bit, what is an electromagnetic wave? You know, what is an an electromagnetic wave is made out of fields, of magnetic and electric fields. And if you want to explain to people what is magnetic field, you have to rely on magnets, on imans, we say in Spanish, right? A magnet, that is a lot of fun to play with them, you know, especially you have to, because they repel each other and they attract in the other way. And you play a lot with that, but you don't see what is going on over there. And you said, oh, it's because there is a force, a magnetic field that goes over there. And then, what is an electric field? That's more complicated. But actually, every time they turn on the light at your home, everything in your home is because you have electric fields going through the cables. We call the voltage, right? But the voltage is nothing but the electric field divided by the distance. It's really the electric field. So these two quantities, the wave is made out of this. So what waves is these two fields in synchrony, one up and the other perpendicular. You know, you have seen people that have seen this with the Maxwell's equation, you know that it is, we call it it's a transversal wave. So what is waving is oscillating transversely in the plane, which is transferred to the direction of propagation. So somehow we make these pictures, and just to remind you very quickly that the wavelength is the size between two lower points, or two high when the wave repeats, and the frequency is that if you stand in one point in the space, then you see that the wave oscillates and is passing besides you and is oscillating. And it's oscillating with a frequency, which is the number of oscillations in 1 second. That's the definition of the frequency. And the unit is hertz, which is the inverse of seconds. So hertz are the inverse of seconds are seconds. And the important point is that the speed of light is a constant, which is the product of these two quantities, lambda nu. Keep that. And so let's review the electromagnetic spectrum. This is a lot of fun for everybody to get. And so the point is that the electromagnetic waves appear in all sizes. We have enormous waves, which are the radio waves that are hundreds of meters. In this axis, I have the wavelength of the waves. So on the big size, we have radio waves, which are from hundreds of meters to a meter, like a human, 2 or 3 meters. We will see, very simple calculation that I will do. But then if we go lower, there are even smaller waves that are the microwaves, like the microwave in your oven at home is like 10 centimeters, approximately 10 centimeters, the size of the wavelength of the microwave. Your cellular phone is around also here, the wavelength is in the microwave also around that. And so this goes from the size of a bee to the size of a pinhead, and so things that we can see with our eyes with no problem. And then we come to the infrared, right? The infrared is in the fractions of a millimeter or to a million of 1,000 of a millimeter, and there's cells and bacteria that we need an optical microscope to see these things. And then it comes, this is amazing, right? That it comes the visible light, which is a very tiny and small region of the electromagnetic spectrum. So light is an electromagnetic wave. This wasn't obvious at all. It was Maxwell with his equations. He found out that his equations had waves. And then he said, yeah, but what is this? Which types of waves are these? And then he looked for a lot of information around about people that were doing electricity and magnetism in the 19th century and before the 19th century. And he was the first ones to really say that we needed a system of units. You see, it was Maxwell. And as a matter of fact, he used the CGS, the centimeter gram second, which for theoretical reason, is better than the international system, but the international system is for real life. But if you do theory, the best system is the CGS. The CGS was used by Maxwell, by Planck, by Einstein. And I use CGS. Don't tell that I use CGS and I'm talking about SI here. But Maxwell wrote his equations, and he found out that his equations predicted waves, electromagnetic waves. And then he went and looked for all the calculations of electromagnetic processes were done in Europe in many places, but with different units. And so he managed to compute all the units and make the equivalence and so on. And then he found, for his surprise, that the speed of the electromagnetic waves was the speed of light that was known at that time. So he said, wow, light could be an electromagnetic wave. This was amazing. You know, we feel that so of course it was known that light was a wave. That was known. Newton had said that it was particles, and now we now say that it's photons. But people had already found, Young and Fresnel and so on had already found that light was a wave. And so he knew that light was a wave and knew the speed of light. And so he said, oh, light is an electromagnetic wave. And people don't believe him at the beginning. It was Hertz who did the first experiments to demonstrate that there were electromagnetic waves different from light and so on. So in his honor, we now call Hertz to this. We should call it Maxwell's instead of Hertz, but that's history. So anyway, then we see only in these tiny regions, that's the only thing, between 400 and 700, 800 nanometers is the size of the wavelength, and here are the colors of the rainbow that you know. And it is very interesting. Although we only see here, we can see with our eyes objects of this size. We cannot see these waves. We can only see these waves. But with these waves, we can see these objects because they are reflected. And our eyes resolve and our brain resolves this. But then we have a smaller, which are the virus. I don't want to talk about virus, but you know, the terrible virus. That's why we are here in Zoom. But the virus are in the ultraviolet size, are smaller than, few nanometers, and so we cannot see those with, not even with a microscope. We need an electronic microscope, which is also quantum mechanics. Okay, and so then we go to X-rays, which is the size of an atom, and gamma rays, which are the size of the nuclei of the atoms, and that's why people that have gamma rays are used for cancer treatments, because they kill cells. Actually, they destroy the nuclei of the cells, and with gamma rays. I don't want to go there. And so I like just to say this, in Mexico City, I listen to a station which is near 100 megahertz, which is called Radio Universal, I guess. And I hear, of course, I also hear one classical music station, they are very near to 100 megahertz. So I like to see this 100 megahertz it means that the waves oscillate 100 million times in second, and this is an FM radio wave. And if we calculate the wavelength as C over nu, we get 3 meters. So that wave is 3 meters now. And this is very large actually, so our eyes cannot see it. And so we go quickly. Oops, my time is going fast. And Max Planck introduced the Planck's constant, but not Planck's constant, introduced H in an act of desperation to explain the black body radiation. This is a talk by itself, and I have a talk like this. You can see it in YouTube. I have a conference that I give on how Planck introduced H. That could have been a talk for this conference, of course, but you can see it over there. And it's a very nice history how Planck is old. He was younger when he discovered. He was 40 years old when he found that the jumps that I will talk about a little bit now, the jumps on the quantum jumps are related by this formula H naught. So we have to see what I'm talking about here. So, but he was forced to do this by experimental data. It didn't come from his head. He was not playing just theory. No. He had experiments that he wanted to explain, very fine experiments that were done by his colleagues in Berlin. And so he was able to explain it. And in order to do this, he had to make this hypothesis. And what is this hypothesis? Now, all the Planck institutes in Germany, right, are in honor of Max Planck. So you should also tell people that the Planck Institute in biology and so on, the Max Planck laboratory and so on, is in honor of this person that introduced quantum mechanics. And this is in one transparency. We don't need to talk much more about it. We don't have to write the Schrodinger's equation. I think this is the essence. I like to insist a lot about this. This was the great discovery, and as a matter of fact, was Bohr. Planck put it, but he didn't realize completely. It was finally Bohr who made the connection between light and atoms. You see the point, that the strange thing about quantum mechanics is that the energy levels are quantized. This is very strange. It says that the energy of the atoms can only be certain values, not values in the middle. It's as if you said that your car could only run at 10 kilometers per hour, 20 kilometers, 30 kilometers, 50, but it could not run at 22 or 24. You say, no, that's crazy. I can run at any speed that I want, just go a little bit faster. So I can make the energy change a little bit for the atom. That's not true. And this is very strange. We have to reflect about this. And of course, we have also the tunneling and all the other things that are, and so on. I don't want to get into that. I believe that this is the big essence of quantum mechanics, these quantum jumps. So an atom can be in one state. I only put two states. It can be in one state and it can jump from here to here. And when it jumps, it emits light. It emits a photon is light. So it has a frequency, and it turns out that the energy is Planck's constant multiplied by the frequency. This is, this equation, actually, if you use it correctly, has inside Schrödinger's equation. That's what Schrödinger did. Use this equation, and with this he wrote his famous equation. And therefore, the change of energy of the atom is proportional to the frequency of the light. And we talked already about the frequency of the light. So there is a connection between electromagnetics, which is light. I say light, electromagnetic radiation, and energy. And here is the point. And also, if we send light in the opposite direction, and the atom is in the lower state, it can absorb the light and make a quantum jump. It cannot go anywhere except to the other one over here. So this is the essence of quantum mechanics, in my opinion, in my humble opinion. But this is the point that I want to make, is that due to modern technology and electronic, we have a great precision in the generation and measurement of electromagnetic radiation, okay? And so here also, now this is more serious. This is the spectrum of the hydrogen atom. It's the simplest atom. It has a proton and an electron. And this is the spectrum. These are the only energy levels. And this was known. The fact that hydrogen emitted light only in these colors was known to Bohr, was known to everybody, but nobody knew why it was that. Bohr said, it's because the atom can only have certain levels and then jump between them. And people said, of course, this is absolutely absurd. But now I'm telling you this as the real truth of life, right? And so, for instance, here, I put here in colors because these are the only ones that we can see with our eyes. The other ones we cannot see. And for this, I have here a video that I made. It's not a very good video, but oops. So this is a lamp of hydrogen. Let me stop. This is a gas of hydrogen, and it is between two ends, which has about 20,000 volts. And so with this high voltage, the atoms collide, get excited, and when they go back, they emit light. That's how your light works at home, the same way as this. But here it is the important thing. So you see this beautiful color, which is purple, something like that. But as you know, this is composed of many other colors. And how we see the other colors? Well, we can bring diffraction grating. People that don't know diffraction grating is a piece of plastic which has a grating, a very tiny grating. And so we open the colors of, this is the spectrum of hydrogen. You can see with our eyes. I took this with a camera. And my movie is not very good, but you can see that this light is composed of all these colors. And so Bohr realized that this was the point. So we were seeing these colors because those were the quantum jumps of hydrogen. And of course, this is like a magician's. You don't see anything, now you see it again, right? And you can see the colors, and you can see these beautiful colors, which has this deep blue and this red, and essentially has all the colors of the hydrogen, has many of the colors of the rainbow over here. You can see here the green, the orange, and so on. So this is the spectrum. You can see it with your own eyes. And so Bohr understood this, and this was with the idea of Planck that energy was quantized. He used that fact and said, it's quantized because those are the quantum jumps. That was Niels Bohr. Okay. So what is the point? The point is that quantum mechanics tells us that all the jumps, you see, all the light that you see, essentially all the light that you see comes from this process. So that's how light comes out of atoms, and how we communicate with atoms is through, I say light, but it's electromagnetic radiation, right? So I want you to, of course, to understand that this is the formula, and of course, this combined with the Broyle's formula that I didn't write. But what I want to insist is that before we measure Planck's constant, now we don't measure Planck constant. Now, Planck constant was in 2019, was defined as exactly this constant with these 10 numbers, no more numbers, exactly this. And therefore, see, now we have the meter and the second, now we have the kilogram in the middle, of course. So we have now a way to obtain the kilogram if you know H, right? So if you know something that you can tell you the meter, the second, then you know the kilogram. This is unbelievable. It sounds very simple, but actually it isn't. It is not. I'm not so sure if I want to go through this. I think already I say this, that very briefly. So in 1990, so the point was that since we can measure frequencies of atomic transitions very precisely, it was about people that say, no, instead of saying that the frequency has some seconds and the seconds will refer to a crystal of quartz, which is not very precise, we better turn it around. And then we say that since we measure very precisely and everybody in the world can have a lab and measure, we have several atomic clocks of cesium-133, then the two specific levels, which is a hyperfine transition, it doesn't matter right now, it's a hyperfine transition. It's a hyperfine transition is a measure of the nuclei, essentially of electronic, but modified by the presence of the spin of the nuclei. And so we define the second in terms of the frequency of the cesium. So we say the frequency of the cesium is exactly, of this transition is exactly this number, and that defines the second. So the second is the inverse of this, is the number of this oscillation. And as I said, we could not be communicating. You could not make any transaction. You could not receive money, send money, go to the bank. Everything that we do, actually, if we don't have this precision, if we don't have atomic clocks, because the communication is through electromagnetic waves that go through satellites. And so we need a lot of precision to do this, okay? And of course, with this, knowing the second and with the constancy of the speed of light, we define the meter. So this, I already said this before. So let me go to the end of my talk. I have 3 or 4 minutes. I said I have 50 minutes, so we can discuss a little bit. So what is the point? You see, in 1976, this guy Kibo is the name of a person. He was also called the Watts balance. I'm confused about the names, but I know that there was one person, Kibo, I forgot his first name, who made this balance to measure H, to measure Planck's constant, right? To measure Planck's constant. And he did this in 1976, so it's been around for more than 30 years. Of course, his balance probably wasn't as precise as the balance is now, but the idea was there already. So it was a device that he invented to calculate, to measure Planck's constant if he knew the kilogram, So what is this formula? You see, the balance, how it works, very briefly, the balance is what you measure as usual. First of all, you balance. So you need gravity. You see, in the balance, in one part, you put a mass of something that you want to measure. You want to know how many kilograms have that, like a balance. You put the one thing here and you put on the other side until you balance. You put weights that you know until you balance. Well, now you don't put weights. What you do is you put a mass and then you equilibrate it. And so you need to know gravity. And you have to measure electronics. And in order to measure how the balance works, when it works, you use Faraday's law and all of this, and you have to make currents, to measure currents and voltages. So you have to make currents and voltages very precisely. And these are measured through the Josephson effect that it will take me 20 minutes to explain correctly. Otherwise, I will just give you, I will send you better to read about Josephson effect. And I forgot the other one. Is the Josephson effect and how we measure the Hall effect. The quantum, I don't think it's the quantum Hall effect, but it was, it was the quantum Hall effect. And so you have to measure very precisely currents and voltages. And these are measured very precisely with Josephson junctions and with whole measurements of currents. And so out of this comes two frequencies, out of the Hall effect and the Josephson effect, two frequencies that, again, we can measure extremely precisely. That's the point. And at some point, part of the process is, in order to measure something, I think they take the weight away, they release the weight, and so the balances start to move. And you put electromagnetic field to make it move at a constant velocity. It's part of the process. And so you have to measure a velocity. So gravity and velocity, this is measured with lasers, the velocity of how it moves. So we can measure the gravity in the place where we are doing this. We can measure the velocity, which is part of the apparatus, and we can measure some Hall current and some Josephson voltage in the apparatus, and it comes out this formula. It's not very hard to get this formula. Actually, it would be like an exam for someone in like a PhD exam, not for undergraduates and first years, but someone in their PhD, they should be able to derive this formula. And if someone wants, I have the derivation in another talk, and a little bit more complicated talk than this one that I also did. And so, but the point is that at the end, Planck's constant appears here. And so Keeble realized that he could measure all of this and the mass of something that he put on the other side, because he knew the mass, and so he could do H constant. But now, since everything is so precise, we turn it around and we say, no. Let's define H exactly as this number. And it was a lot of discussion how this number should be fixed. You know, and that was part of the problem, that people that were doing this in Paris, these were scientists like us, you know, of course, probably more famous than us, of course, that were doing this in Paris. It was a colleague of mine that was there in this conference, and he said that it was a very strong discussion, that some countries, I don't want to say because probably this is information that I shouldn't say, but some countries were completely against this, that this was done. So it was, again, it was arbitrary. So these people, with their measurement, say, let's define what Planck constant is. And they came with this. I think there was discussion about the last figure. It was 50 or 49 or something, I don't know, 51. But finally, they say, we're going to use this. It's 10 significant figures. It's a lot of figures. And with this, then put it over here, and then we know the mass. And we don't have a prototype. Then the Grand K Le Grand K in Paris disappears. The kilo in El Kilo in Paris disappear. And now we have this form. So it is, as I said, it's a nice exercise. I could actually look for it right now in another talk if you want to see it quickly. We have 5 minutes or so. I don't think so. And now we say, but this is interesting because we now say H is a fundamental constant. So it must have a number. It cannot be something that we measure. On the contrary, it should have a number and we use it. The same with the speed of light. It is a number. And we are missing the third one, right? The third one would be the gravitational constant, but we don't know how to join quantum mechanics with gravity. We're still struggling with that. And hopefully some of you will work on this, and probably some of you will tell us the answer in the future. I hope so. So to end my talk, just let me tell you, it was not only H that in May 19, 2000, and they chose May 19 because it had been the same May 19 of 200 years ago. And so it was symbolic to use May 19th of 2019. It was before the pandemic. And not only H was fixed, it was also fixed, the electron charge. So the electron charge has exactly this number in coulombs. The Planck's constant, Boltzmann constant, which is this one, and Avogadro's number, right? Avogadro's number, you know, we always use 6 times 10 to the 23. Now 6.221476. We have all these figures. There's a few figures. These are not many figures, but this was the convention. And it was interesting because probably there was a Nobel Prize that came to Mexico, William Phillips, and tells us about this a little bit. And he says that this will last now forever, which humbly, I doubt that this will last forever. I'm sure that we will make changes, especially the second will change. The second is about to change because now we have what are called light combs. Comb, C-O-M-B, light combs. My English is not very good. Light combs, like combing your hair. Light combs that can, that now have more figures that can be expressed with our current second. So we are in trouble. We have measurements that are more precise than our own second. So probably the second will change and this will go start changing and this probably will be fixed in the future. You know, this is, we humans will not stop. And the point is that we no longer use physical prototype. This is important. We now use the laws of nature that we believe we know in order for them to give us the numbers that we need for describing them. It's a little bit crazy. That's the way it is. Okay, my time is up. I thank you very much for your attention.
Thank you very much, Doctor. First, I want to apologize because of the trouble with my audio at the beginning.
It's okay.
It was awesome, your talk. And thank you for sharing with us your knowledge and your time. If we have time for one question, please, you can activate your microphone and ask the doubt that you have. Well, I have one question.
Yes.
Who decide when is the time to change how we measure some?
No. I think that question is very important. And this is the point that I wanted to say before. You see that the second now, it has like 9 figures. Our second has, our current second is over here. Here, the second has 3, 6, 9, 10 figures, right? So it's now there are measurements with optical measurements because we can measure frequency unbelievably precisely that has more figures than this second can express, reproducible. So many people can reproduce not 10 figures or 12, but they can reproduce 14, 15 figures. So the second is not enough to describe this. So you have a conflict between what you can measure, because then what is the meaning of what you are saying if your ruler does not have sizes, right? If you want to measure, if you have a ruler, a normal ruler, a 30 centimeter ruler, that it has millimeters as the slowest, as the smallest measure. If you have something that is smaller than a millimeter, you cannot measure it, right? You cannot. You have to take a micrometer and measure. So if you have a ruler, you cannot measure something that is smaller than a millimeter, a normal ruler. So the same is happening now. And so when this conflict is so strong, then these people get together in France. There is a conference and they invite Nobel Prizes and very famous people, physicists most, that we know from their papers. They get together and say, okay, what do we do about this? And they fight because some people say, no, we have to wait. It have to be something that it can be reproduced and it can be very, very strong. How you say, have a lot of strength, that is solid, that is robust is the word. Something that is very robust. And so the kilogram, people had decades saying, come on, we cannot keep using a kilogram, a piece of metal that is in Paris, because that thing is evaporating. So it's losing weight. So what is really the kilogram? That was the problem. But they couldn't find one way. And so they came with the Keeble balance, and the gossip is that there were people in this conference that they say, this is not completely robust, and there's too many things to measure. And they had a scientific fight. And then at the end, it was a vote. People raised their hand and said, who voted for this? I voted. And so all the countries that were there represented at the end voted. So at the end ends up as a democratic activity. It's very interesting. But when it is happening is when you have conflicts between the precision of your measurements and the ruler with which you are measuring. Then you have to do something about it. You have to make a decision of how to change it. You see my point? I think that the problem with the previous kilogram is that it was very imprecise when people were trying to measure things in the micrograms, in a million of a gram. I think that was part of the problem. That the balances that people were using could not be, they had problems with very, very tiny measurements. And so they say, we have to change this. It's too much. Not to measure a kilogram of tortillas, right? It doesn't matter. 1 or 2 tortillas more or less doesn't matter. But when you are measuring things that for medicine and so on, then, or for very sophisticated experiments, you have to make a decision. It's a very complicated issue. Thank you.
Yes. Thank you very much, Dr. Victor Romero. We are on time for our
There are 2 questions here.
Yes, but we.
Oh, yeah, you don't have time. Okay.
We can have 1 minute.
Let me write here in the message for everybody.
Okay.
My
email.
My email, please.
Yes,
you can write. This is precisely my email.
Okay.
My office, so you can write to me anytime.
Please.
And I will answer details, and I hope that the talk was not too superficial. That's only my preoccupation. I hope it was more like a conversation, as I said.
It's awesome. Thank you very much.
Thank you.
Also, we will continue with our next activity, what is the dancing class of the Latin rhythms, and in the other link by Zoom. So see you in the next link. See you, Dr. Victor, and thank you very much.
Thank you very much. Thanks to you. Thank you.
Thank you.
Bye.